I want to open the algebra talks by talking about what is really a very algebraic approach to a problem which, to some problems which also have geometric meaning, but the algebra does add something to the picture. Namely, I want to, this is, I should say before I forget, joint work with Alain Hainaut. And I want to consider linear differential equations. That is, from an algebraic point of view, I want to consider a connection. So we write it this way, where here x is some algebraic variety, which for purposes of this talk you can think of as an algebraic curve. And E is a vector bundle on x. And a lot of the interest comes by permitting the existence of my connection to have poles. So I maybe for the moment I just put a star here to indicate that the connection can have poles on some divisor of x. So I remind you that a connection, I want to consider integrable connections, so nabla squared should be 0, and it's basically just a way to differentiate sections of a vector bundle. Okay. I work over a field, I should say, for the flat connection. It's a flat connection, yeah, integrable connection. I work over a field K, which is algebraically closed, characteristic 0. But sometimes, and I may indicate this by writing rather than lowercase k, I might write capital K. Sometimes I want to assume that my field K has some parameters in it, so that it makes sense to talk about differential equations over K, over capital K. So you can think of this as being the complex numbers with some parameters. Yeah, you're right. Forget this. Or maybe, well, it'll be clear. No problem. Okay, now Gromov very correctly put his foot down early in the conference to say that we're not allowed to talk about things that don't exist. And we're not allowed to talk about things that you don't have a mechanism for constructing a lot of. So there is a sort of a standard mechanism for constructing such a thing, which is called the Gauss-Menin connection. And just briefly, what that involves is you take some other algebraic variety y, which you suppose sits over x, and you construct your bundle E as being some higher derived image of the de Rham complex of y, like this, omega dot y over x. In other words, you take the bundle whose fibers are the de Rham cohomology of y over x. And that, well, it won't...
The forms along the fiber?
Yeah, the forms along the fiber. And if the fibers are smooth, that forms a bundle. But there can be degeneracies, in particular there can be poles, when the fibers acquire singularities. Okay, but for my purposes, that's not very interesting. Because there's a classical theorem of Griffith's that says that such an object, the connection has what's called regular singular poles. Okay, so that means that when you put the poles in here, if you set things up correctly, you don't have to take very big poles. And for purposes of what I'm doing, I'm interested in the situation when the connection when the differential equation has larger poles. So this has regular singular points.
Like dz over z.
Right, like dz over z. So dz over z. And it's not that those are uninteresting. They're very interesting. But this conference being aimed at the future, one should think about the other case, where you have irregular singular points. So maybe I won't write it there because of this. So what about the case of irregular singular points? And that means that your connection dz over z to the m for some m at least 2. And that, well, I mean, it means more than that. It means that it has that kind of a pole, and that by clever manipulation, you can't do any better. You can't get it down to 1. Okay. So the point is, philosophically, and we're supposed to be philosophical at this conference, that the theory of motives. You see, I mean, what did I do? I took a variety y over x. And we're taught now to think that, that really there's much more data than just the de Rham cohomology. There's a whole, what you might call a motivic sheaf on x associated to that data. So you have because for example, you could take the L-adic cohomology, the sheaf of L-adic cohomology groups. And that would give you a representation of the arithmetic fundamental group, or the algebra geometric fundamental group of X. So there's more data than just a connection. But unfortunately, the connections associated to motivic sheaves always seem to have these regular singular points by Griffiths. So if you are interested in irregular singular points, you have to abandon motives. Or so it would seem. I have no clever idea how to combine irregular singular points and motives. But we'll see that even in the irregular singular point case, there's a sort of a motivic flavor that frequently bubbles up, in the sense that you have a unity of data, both arithmetic and geometric, a remarkable unity of data that we don't really understand, and that I really propose is somehow the problem, the theme of this lecture. So perhaps under irregular singular points, I'll write motivic, what do I say, motivic properties.
Have things evolved now that you can use this word without saying something about what it means?
It's kind of like, Dennis, it's kind of like the smile on the Cheshire Cat. I mean, every time you talk about it, you try to give some picture of the smile, and nobody has ever really seen the cat. So I try to show you a little bit of, I mean, in fact, I don't, because we rapidly drift away from motives. But
more like the smile of Schrodinger's cat.
Well, yeah, but Schrodinger's cat wasn't smiling because he was in trouble. But anyway, maybe the frown on Schrodinger.
Write down now to be the definition for the.
No, I'm not going to. I'm going to go away from. I'm going to. The next word I'm going to write is no. Okay.
Forget it.
Right, but still interesting patterns linking. Well, that's what we're going to see. Well, maybe, I mean, that's what I'm going to try to show you. Linking arithmetic and these differential equations. Okay. Now, there's one more idea one more basic idea that I want to introduce, and that is the idea of what one could loosely call the epsilon factor. Okay. So I'll put it in quotes because it's not really precise in the context. So let me talk about two different situations, and let me fix ideas. I'll take x. Now I will take it to be an algebraic curve over a field. Maybe I'll call the field capital K. And I'll give myself a divisor D on x, and maybe I'll write x naught and j for the open complement. So x naught is x minus the support of D. Okay. So there are two different situations that I want to sort of commingle. Sorry? Yeah. MIs are greater than or equal to 1. There are two different situations that I want to kind of commingle. The first situation, call it 1, is a situation where this is a curve over a finite field. So this is where capital K is some finite field FQ. And I have some L-adic sheaf. Don't worry too much. I'll give an example in a little while. If you don't swing with L-adic sheaves, don't worry too much about it because it's not the main point. But for those who do, let's suppose that I have, call it say F naught, an L-adic sheaf on X naught. And then what one typically is interested in, well, I mean, one thing, in some sense, the simplest thing of an arithmetic nature one can ask about this F naught is the so-called epsilon factor. And if you're a geometer, maybe you'd rather think of something like the Quillen determinant. Because what it is, the epsilon factor, is basically the determinant of cohomology of this sheaf. So in other words, you look at the determinant, that's just the highest exterior power, but your cohomology comes in graded pieces, and so you have to keep track of alternating signs and things of that sort. But basically, it's the determinant of the cohomology for the étale topology on X, but I pass to the algebraic closure, and then I take the direct image of this sheaf, F naught. Now, what is that? Well, this is an L-adic sheaf, so that's a line, and an L-adic line. It's not a very interesting thing. It's just a line, but it has one bit of structure. Because the sheaf F was defined over the smaller field FQ, you should think of FQ as being like a circle. And because the field, you sort of have it's like a Seifert bundle, and so you have an action of winding around. So this comes equipped with a Frobenius automorphism. And the epsilon factor is just minus the Frobenius acting on this determinant. Okay, so epsilon factor. So that's the first.
Element of the field.
Yeah, so it's a number. It's an L-adic number. L-adic number. Oh, well, I haven't made any assumptions about my sheaf or anything, but very typically it will be algebraic. Okay, so the second thing, which is really the direction that I want to study, is to take K, as I was saying, some function field. And in this case, to take for F, or F naught, I call it E over here, E naught, with a connection. with an integrable connection. But now we have to be careful because there are parameters in the base, and I want to be able to differentiate with respect to parameters in the base. So this is a little bit more data. So you can talk about a connection. This is nobla is what's called an absolute connection. Yeah. It's in QL bar star, actually. L-adic sheaf, technically, you permit yourself to go to the algebraic closure of QL. So if you like, this is an element in QL bar star. Okay? So now I want to talk about the geometric picture. I want to take an absolute connection. So that means I permit myself to, it's a lot richer data. My x was a curve. So to give yourself an integral relative connection is not that much data. Because, of course, if you talk about a relative connection, omega 2, the two forms are 0. And so the integrability condition is empty. But for an absolute connection, it's not empty. So I assume that nobla over the whole family, exactly.
Where it's not supposed to be flat.
Yeah, no, it is supposed to be flat. On the whole family.
Absolutely. Flat along fibers.
Well, no, but I'm asking the whole family.
Yeah. Technically, you can weaken it slightly to assume that it's what we call a vertical connection. So that means that when you look at the flatness equation, the only part of it dies. But let's not get too. Let's assume that it's actually flat. But so that induces a relative connection, which I write this way, from E naught to E naught tensor omega of x naught. To distinguish between the relative differential forms and the absolute differential forms, I'll write omega 1 x. These are the absolute forms. So that surjects onto omega of x, which are the relative. Okay.
Relative, again, is forms along some fiber.
Forms along the fibers, exactly. Okay, so here again, because you have an absolute connection, you get a connection on the de Rham cohomology, on the relative de Rham cohomology. So nobla induces connection on the H star x over k de Rham. Yeah, I'm going to... Sorry? Yeah, so in other words, let me explain that a little more carefully. In other words, what you do you look at your bundle E naught and you go via your connection to, but you go via your relative connection, sorry, to E naught tensor omega x naught, and that gives you a little two-term complex of sheaves. But if we seriously assume that, which we'll want to assume, that our divisor is non-empty, so maybe let me add a condition here, this should not be the empty divisor, then your curve is affine, and so to calculate by sort of known business, it's a Stein space, to calculate the cohomology, you just take the sections. So in other words, you take algebraic sections of your bundle, and you apply this connection, and you get a little two-term complex, and you calculate its cohomology. And so the cohomology of this little guy is the de Rham cohomology, by definition, I just write E or E naught. Okay, relative de Rham. So I should put it over K. And because
Omega now means all the forms of all dimensions, right?
this is, well, I mean, I'm assuming that X is a curve. So
0, 1, 1 form.
0 forms and 1 forms. So here are the 0 forms here. And here are the 1 forms. So, but because we assumed that we had an absolute connection, these groups here inherit connections. So you have what are called the Gauss-Manin connection again on the de Rham cohomology of okay?
But now this connection lives over the family.
Over K. This connection now lives over K. Tensor omega 1 K. K. We've pushed it downstairs. See, these are K vector spaces.
K is the base of the parameter.
K is the base.
K is the base.
So you see, algebraically, it's in some sense, when you work with connections, you don't lose that much localize. It's technically extremely convenient, and you also don't lose that much to localize to the generic point, because a connection kind of propagates, and if you know what it's doing at the generic point, you know everything. Anyway, to tie up with the previous discussion, in the case of a curve over a finite field, we took the determinant of cohomology. So we can also here take the determinant of cohomology. And so we can look at the determinant of the Gauss-Manin connection on the determinant of the cohomology. Okay, so this guy is just a K line. So he's just K. And somehow we've got some connection on K. So that means a connection just means you talk about... Sorry? So let me just finish my thought. Maybe this is determined nabla Gauss-Manin of 1, so to speak. If I choose a basis for my one-dimensional vector space, call it 1, then this is just some element in omega 1 of K. Okay? I'll give some examples in a minute, but the point is that the isomorphism class of this determinant. See, we've got to be careful here, because when I write this, I've chosen a basis. Now, what happens if I change the basis? Well, if you look at the connection formalism, the effect of changing the basis is to change the element by a logarithmic derivative. So in fact, what's canonical here is an element in omega 1 K modulo let me write d log of K cross. So by d log of K cross, I simply mean the collection of all elements df over f. Okay, so those are the actors.
So these only depend on singularity, yeah? So this class depends on the...
No, maybe I want to show some slides here, but maybe since you raised that question, let's talk a little bit about this class here. So let's first of all look at the simplest case, where I assume the divisor D was non-empty, that is, that we had poles. But let's look at the case where we don't have poles.
How big is that?
Well, for example, just to give you a feeling for it, suppose that K was C Laurent series in T. Then what you would have is a map, basically the exponential integral. You'd have a map from this thing to C cross, which would send a form, let's say eta, to the exponential 1 over 2 pi I integral of eta.
So it's a residue at this point.
Yeah, it's a residue. Residue, not here. I'm doing it backwards here.
It also depends on the position of flow.
Right. So I want to. What am I saying? Yeah, you have a residue. That's maybe the best.
What about it, though?
Well, I mean, it's the monodromy. You're leading me in a direction I don't particularly want to go, but that residue, the exponential of that residue. See, in other words, if you take the residue of a logarithmic form, it's integral. So I miswrote it, but you have a map here which sends eta to the exponential of, well, depending on how you define the residue of eta.
This quotient depends only on behaving poles, yeah? Where omega is regular, this thing can't cancel each other, no?
This discussion here, let me, it depends. You see, the problem is when you say that, there are two things you can think about poles. You can think about poles, as I was mentioning, sort of horizontally in terms of the divisor D, or you can think of them vertically because you localized here. You're right that the vertical poles play a role here. Okay, I don't want to get too far.
As you pointed out, this form is not closed in general, right?
Or maybe flatness is like it.
This is a deep question, and we can, in fact, prove closedness results. But flatness does imply closedness, but you have to be.
Again, everything depends on the poles, yeah? Right? This is motion space only tells you what happens at the poles. If the regular points is just the same, right?
Well, in a local, maybe we talk about that later, because it's almost true what you say, but there's a. Yeah. Well, I think an image to think about, this is the simplest image to think about, is the exponential of the residue, which is the classical way of calculating the monodrome. Okay. Right. So I wanted to mention the simplest case when there are no poles. So let's assume that D is empty for a minute. Then I want to give you a formula, a Riemann-Roch formula for the epsilon factor. And this formula applies mutatis mutandis in both cases, both the case of a finite field and the case of the geometric case. And the formula is the following: you take your you take the determinant of your sheaf E inverse, and you intersect it with a certain characteristic class, C1 of omega, whatever that means, and that is equal to the determinant of H star. Okay, can I abbreviate that? So what does this mean? This means you have some kind of a bundle, either L-adic or geometric, upstairs. The C1 of omega is just the omega is a coherent sheaf. We take its first characteristic class, which is a divisor. So this is a certain divisor. If you like, you can think of the following. You take eta, a meromorphic one form, and you just simply take the divisor of this eta. That divisor represents this C1. And what does this mean? You take this determinant, whatever it is, L-adic sheaf or sheaf, rank 1 sheaf with connection, and you restrict it to these points, physically. Restrict it to these points, and you tensor the whole thing together so that you get a line, and that's the answer. That's the determinant of cohomology. So you see, it's a Riemann-Roch formula for two reasons. First of all, the data here is upstairs. The data here is downstairs. This is, so to speak, the first characteristic class downstairs. And secondly, and this I particularly want to emphasize, secondly, there are two pieces here, and this one depends on the bundle E, whereas this one depends only on the geometry of the curve. Okay? That's a very simple case. But now suppose that we have irregular singular points. Then this no longer holds. Okay, let me now... Yeah. You see, that's right. I mean, it's not usually thought of that way, but in fact, that's what it is. And I could go further, but time is a little bit tight. So let me push on here. I want to show you some slides. So now let me go back to the point I was trying to make earlier, which is the essential unity between these two cases, between the epsilon factor in arithmetic, that is for a curve over a finite field, and this geometric object. So let's see if I can make this work. What I'm going to show here is some results of Terrasoma. They're not due to us. They're due to Terrasoma. And let's see if I can explain what's going on here. Terrasoma considers, first of all, let's look at the geometric data. So it's going to be a rank 1. Our bundle, our E, capital E, is just the trivial bundle, the structure sheaf. The curve X is a projective line. And he gives himself a collection of real numbers, lambda k. And he defines a connection on the structure sheaf by nabla of 1 is, as indicated, the sum sk, and then the logarithmic derivatives, plus d of capital F, where capital F is some polynomial. Now this thing has what's called an irregular singular point at infinity as long as capital F is at least degree 1. So in other words, the differential form that you see on the right has a pole of order at least 2 at infinity, and you can't do better. You can't get rid of it. So now he doesn't actually, he does something slightly more precise, or not slightly, considerably more precise than what I'm talking about here. He looks at the periods, the determinant periods. So let me see if I can give the... So he computes the determinantal period. So that's essentially like taking the connection that I explained down on K, the rank 1 connection, and taking a corresponding horizontal section and taking a pairing of the algebraic with the horizontal section. So this is sort of a period that he's computing. It's a number. It's not a differential form, but it's obtained by integrating that differential form against the period. And so there's the shape of the answer. It's some complicated but not totally unexpected things involving differences of the real numbers lambda and exponentials of f of lambda, and then the exponential of f of u at points where the derivative, I don't know if you can see it, the crucial, as usual in mathematical formulas, so often the crucial thing is the absolute smallest thing in the formula. That little prime there is the crucial data in the whole slide. You look at the points where the derivative, where the f, capital F, has a critical point, and so there's a formula. And now here's another formula, also due to Terrasoma.
Can I just what again the meaning of this in simple terms? What this formula tells you? This formula has got a formal meaning, yeah.
Yeah, it's a period. Oh.
No, but just forget about it. Just about the identity, what it is.
Well, I mean, I don't know what to tell you. I think that the answer reveals itself. I mean, it's like peeling an onion. There's no absolute answer. What does a formula mean? But the point I want to make is the analogy with another formula, which of course you can't read. But now let's go over to the finite field case, where the analog of this connection is a rank 1 L-adic sheaf, which I call f of chi, and it's defined by a character chi of the Galois group. Oh, k is unfortunate. I'm sorry. Capital K is playing two roles here, so maybe capital K should be an L there. Let's see if I can call this. This should be capital K. It's the function field of the curve. Let's see if I can put a little x here. Don't know if that makes it.
Where's the irregular singular point?
At infinity, Dennis. At infinity. Here, what replaces the irregular singular point is a wildly ramified character, and I'm afraid I just don't have time to explain. If you're comfortable with class field theory, you'll...
What do you mean widely ramified? Why it's widely ramified?
Well, because it's not tamely ramified.
It's character of the Galois group. It means the corresponding extension is widely ramified. It's not tamely ramified extension. The kernel of the character which gives you.
It means, roughly speaking, that it's difficult to understand, whereas the tamely ramified one.
Tamely ramified, it essentially behaves like a complex number. There's no specific guiding properties.
Okay.
If it gives root of p, then it's something that we shouldn't see.
Right. It's not something geometric, in other words. And the description of the character is here. You take your same f. Now, this is the link with the previous formula. You take the same f, but now you reduce it mod p to view it as a polynomial over a finite field. And you look at the rule, which is a character, which associates to an element y in the multiplicative group of the field, the residue of f times dy over y, and then you take the trace. And then a crucial bit of data you give yourself, this is always important, an additive character of the finite field. So the chi, the capital Chi is a product of this ramified, of this wild character, phi, with some tamely ramified characters, chi I, at the points lambda I. So now lambda I, which over there were real numbers, are now points on the projective line over a finite field. And G is the Gauss sum, which is just the sum of the multiplicative character times the additive character. And then Terrasoma's formula, which I hope you can read. Maybe if I sort of tip it up here a little bit, it might be a little more legible.
Now you can't.
Now you can. Well, what can I say? Is that better?
Yeah.
Okay. Maybe. Well, the point is, I want you to look. I want your eyes to drift back and forth between the two sides, because in fact the formulas are quite parallel. You see over here where you have a 2 pi. Here you have a q, where q is the number of elements in the finite field. Over here we have gamma factors. Here you have Gauss sums, and so on. Actually, there's one bit that doesn't quite match, and I'm a little bit confused about. It's this factor here, and I have to admit, we're sort of trying to shove that under the rug. But everything matches, and notice the interesting thing where you see an exponential here, you get this additive character here. So the philosophy, I know it's difficult to absorb precise mathematics in this situation, but the philosophy is quite clear that the exponential is related to this additive character, the Gauss sums are related to the gamma factors, and there is a quite tight dictionary between the two formulas. So this is a formula I stress for the epsilon factor. This is a formula, if you like, for the period of the rank 1 connection given by the determinant.
Is this the motivic?
Yeah. You see, this is the, well, motivic in some philosophical sense. It's not like a motive. Motives don't behave this way. But there still in all is some link between the geometric and the arithmetic case. Okay, I'm more or less running out of time here. How much extra time do I get? 5 minutes? Count 5 minutes? Okay. Oh, that's cool. Wow, that's fantastic. Yeah, right. Okay, so I want to state one other. I want to state a theorem, and to state the theorem, so maybe we can shut these off now. Has everyone absorbed all the, sucked all the juice out of these beautiful formulas of Terrasoma? Yeah. Well. Okay. So now let's look at the. See, what we're after is a formula for the epsilon factor. We want a formula, and in the classical epsilon factor situation for a curve over a finite field, it's very difficult to imagine a formula, because what would you put into the formula? There's sort of no, you don't have any, it's very hard to generate invariance of the situation. But let me point out in the geometric case, there is a very nice invariant, which is the following. You have nabla, and now let me write it slightly differently. Let me write it this way. In other words, rather than thinking of it on the open curve, I'll think of it on the whole curve, but I'll permit poles. So this means that my connection has poles. Now, when I have a gadget like this, what I can do is restrict it to the scheme D. So in other words, I can write OD as OX modulo OX of minus D, divide out by functions vanishing to order mi at xi. And then if I do that restriction, so let me write ED equals E tensor OD, then I get a restricted map, ED, and it does something that connections don't usually do. Namely, it becomes function linear. So let me write it as E tensor omega x of D modulo omega x. So I take differential forms with poles on the divisor D modulo the regular forms. And this guy here is usually written omega sub D. It has some algebraic interpretation as a dualizing object. So this then becomes E tensor omega sub D. And this induced map from the connection, yeah, you take the principal part, if you like, of the connection. So this is the principal part. Let me write it nabla D. And the point is it's function linear. It's function linear. Okay.
Write another D under the E?
Well, you could if you wanted to, yeah. If you like that better, yeah. Now, since time is more or less up, let me just do two things. Maybe three things quickly. So first of all, theorem. Second of all, formula. Third of all, blah, blah. Okay? So theorem is the following. Suppose that the rank of E is 1. So the rank 1 case. So here we can actually give a formula for this epsilon factor. And it is the following. The determinant of H star theorem, E nabla K, in the sense that I explained before, that is, as an object is a line with a connection, is given by the following. You take the determinant of E inverse, and you restrict it to, say again? Yeah, it would be, yeah, sorry, determinant, right. It's just E. I don't know if it's clearer to leave it this way, or let me leave it this way because the analogy is, it's just E inverse. And then you multiply that by C1 now omega D, and now you put in, as usual, the interesting bit is the last bit here, because what am I saying here? Nabla was, as indicated, nabla D, and when E has rank 1 and nabla's function linear, you can, so to speak, cancel the E. So nabla D becomes a map from OD to this principal part, this omega D. And if I'm careful to choose my D minimally, so that the connection has a pole of order precisely the indicated multiplicity, this map will actually be an isomorphism. So that this map will give a trivialization. This is omega poles along D, restricted to D, So we're now in sort of a classical algebra geometric situation. We have a line bundle, we restrict to a divisor, and we have a trivialization. Okay? Now, when you have that, you can choose meromorphic section of omega d, which agrees with this trivialization at d. So you just simply choose eta meromorphic form with poles of order exactly d and agreeing with this connection. So let me just say agreeing with nabla d along d. Well, it means the principal part. So this is a form with a principal part. It means simply that the principal part is the same. Okay? And so then the theorem is that simply that you just take this you take this bundle upstairs and you restrict it to the divisor of eta. Okay. Again, just in the naive sense, this is a collection of points with multiplicities. You take the line here, you restrict, you tensor them all together, and you get a line, and that's the right line. Okay, now to the formula. So this is the theorem. The formula, I write it down because it has an interesting flavor. Now let's no longer assume that E has rank 1. Then I have to give myself a little bit more space here. The formula is simply this, that you look at, suppose now that the
What is the S root is here because
say it again?
a command on this field.
Well, the point is, if you like, if I had more time, I could have explained more. The point is that there is no known formula. There are local formulas for the epsilon factor in the rank 1 case.
Because there are lots of analysis, lots of Bismuth type formula. There are lots of formulas.
Not in the case of wild ramification. The point is, you're letting your geometric intuition get away with you. The first time, whenever anyone teaches a course in irregular singular point differential equations, the first thing you learn is that it does not correlate with the geometry on the open set. That is, any rank 1 connection or any local system on the open set extends to a regular connection. But when you have irregular connections, there's no geometric interpretation. So this is richer than the theorems, than the geometric theorems of Bismuth and such people. Okay, I'm really out of time. Let me just write down the formula here. In the higher rank case, you look at the determinant of E inverse, and then you dot it with C1 of omega of D with some, you just choose now some trivialization. And then I just wanted to write down you take the residue of the trace of dg G inverse times A, where finally A is the connection matrix, and A is of the form G dz over Z to the M plus eta over Z to the N. So you have to make so the conjecture is that when the poles when N is less than or equal to M minus 1, and when G is an isomorphism, then star here, then star gives the determinant. Okay, I'm through. I think I'll spare you the blah blah.